Hello everyone, we are group 14 and our topic is prompt to prompt image editing with cross attention control. Now, this research is mostly focused on editing AI generated images. So, you see, one of the biggest problems with editing AI images or any image in general using AI, using prompts specifically, is that a single word can effectively change the entire image. So, for example, here I have an image of a cat riding a bicycle, and I simply change the prompt saying cat riding a car. Now, this image is totally different from this image. In fact, the cat is also different from this image. Now, the reason why this happens is because of something called the butterfly effect, which means that a single word can drastically change the composition of the entire image. So, the one of the existing solutions for this is masking. So, masking is basically where the user explicitly tells the AI through the prompt to focus on a specific area without and it basically ignore the rest when it comes when editing an image. The problem is this places a burden on the user and sophisticated tasks such as retexturing a surface is not possible with this approach. Now the solution they have come up with is using cross attention control to effectively uh, to effectively automate the masking process during early composition.
Before explaining the technical method, let us compare traditional image editing with prompt to prompt. On the left side of the presentation, traditional editing methods require the user to manually draw the spatial marks. These methods do not fully use the internal relationship already learned by the diffusion model. Fine-grained changes are difficult and the user must spend additional time identifying the correct image region. On the right side, prompt to prompt provides the text-only editing interface, and it reuses the model cross-attention map, preserve the overall composition and layout, and it does not require the retraining or fine-tuning. So the main point shown at the bottom is the prompt to prompt control the image through word to region attention rather than manually drawing masks. So to understand this relationship, first we need to understand the cross attention. So this is the most important technical concept in our presentation. On the left slide, explain the query key value so that the spatial image features are represented as queries and the text token from the prompt are represented as a key and values. In the center, we can see the attention map formula. You can see the M equals the softmax of Q multiplied by K transpose divided by the square root of D. The resulting attention map show the how strongly each image region is influenced by each text token. On the right side, we can see example based on the prompt, a bear sitting on a rock near a bird. So the heat map of the word bear shows the strong attention around the bear region. The heat map for the word bird show the strong attention around the bird region. So this relationship is known as pixel to token binding. Therefore, cross attention acts as a bridge between words and image regions. So moving up the next slide. So the key observation. So the authors made an important observation about the diffusion process. At the top of the slide, the timeline begins on the left with the random Gaussian noise and gradually moves toward the final image on right. During the early diffusion step shown on the left and the middle of the timeline, the model decides the approximate object position, scenes, geometry and overall layout. The later steps show toward the right mainly refine texture, color, lighting and fine visual details. At the bottom of the left, we can see the using same random seed alone does not reliably preserve the original composition. At the bottom right, we can see that injecting the original attention maps during the early diffusion step helps preserve the layout while change the requested concept. Therefore, that the early attention control is the foundation of prompt to prompt.
So, moving forward, let me now take you through the prompt to prompt framework. The traditional image editing requires users to draw masks or select specific regions, which is a time consuming process. The prompt to prompt framework offers a simpler alternative. Just change the text prompt and the image updates accordingly. The core idea behind this is the diffusion models internally create cross-attention maps, and we are going to reuse these maps from the original image during the new image generation. Therefore, the overall structure and layout of the image is preserved. And importantly, this requires no retraining, no mask, as well as it is compatible with any diffusion models. And there are three applications. The first application is word swap, where a single word in the prompt is replaced while keeping the rest of the image unchanged. To achieve this, the attention maps from the original image are injected during the early diffusion step to preserve the overall composition. After a certain threshold, this constraint is relaxed, giving the new word enough freedom to adapt the image to its meaning. So as shown here, replacing the basket with bowl or nest only changes the container part. And if we modify the apple with either cookie or orange only changes that target objects, while everything else remains the same. The second application is prompt refinement, where new words are added to the prompt, and in this case, the original attention maps are preserved only for words that appear in both old and new prompt. New words are free to generate their own attention and influence the image independently. For example, adding the word squared or colorful only affect the sunglasses, while adding beer or coffee only affect the drink. So while the rest of the image stays same.
So my teammates covered how to subvert and add new faces. The third application is attention rewidening, and the idea is very simple. Say you have a fluffy red ball and you just want it to look fluffier. You don't want to change the prompt, you just want more of that one word's effect. This is the formula introduced by authors, and meaning is very simple. So you pick a word and multiply its attention map by a number c. Above 1, the effects are very strong. Below 1, effects are get very weak, and nothing else in the image changes at all. Here are real examples from the paper. Every row uses the exact same prompt, but only C changes. Turn down birthday, the cake loses its candles. Turn down blossom, the flowers disappear. Turn up snowy, more snow on the mountain. Turn up floppy, thicker fur on the bunny. Same prompt every time, no mask, no retraining, just one number giving you control how strong a concepts look. So, what did the paper achieve overall? The key discovery is that attention map tell you where each word lives in the image, and you can use that to edit without any mask. The three moods my team presents today: WordSap, adding phrases, and reweighting. It covers wide range of edits. And with DDIM inversion, all of this works on real photos too. The authors are also honest about what they doesn't work yet. Real photo reconstruction isn't always accurate. The attention map are low resolution, so precise local edits are hard, and you can't move objects, only change how they look. But the paper describes itself as a first step toward editing image just by changing words one step at a time, and I think that's a pretty exciting direction. Thank you.